Hi, my name's Peter. I'm a PhD student at Oxford, and I'm currently visiting Michael L. Burgo at Harvard. And this was co-led with Adi. And then we also had a lot of help from our team, Abbas and Alvaro, and then my advisors, Michael and EY. And so today we're going to be presenting meta flow maps. And basically just the pitch in like 2 sentences is that if you want to do reward alignment of your base diffusion model or flow matching model or flow map or whatever, usually that's going to be really expensive. And so what we're proposing here is if you do a little bit more training to get a meta flow map instead, then any downstream reward alignment, whether that's during inference time or fine tuning, is going to be much more efficient and much more scalable. And that's because we're going to unlock these one-step posterior samplers. Sorry, can you see my screen, by the way?
Yep, all good, all good.
Okay, perfect. Let me go
So, well,
into,
I'm seeing a PDF right now in the
yes,
PDF view.
okay. Let me go into presentation. Is this better?
Yep. Now we see a nice little single slide.
Perfect. Okay, how do I? There we go. Okay, so let's quickly just review generative modeling really quickly. So in this setup, right, we have some prior distribution P0, such as the Gaussian distribution, and we have some data distribution P1 that we're going to assume we already have a collection of samples from. And our goal is to learn how do we transport samples from P0 and transform them into data samples from P1. And we want to learn some transport parameterized by a neural network to do this. And we want to learn this transport using that existing data set of samples that we have. Now, there are many different ways that people have thought about doing this, diffusion models, flow matching, and I'm just going to stick to the notation of stochastic interpolance, but all of these methods are very related. And in stochastic interpolance, what we have is that we're going to take our prior sample, I0 from the Gaussian, and our data sample, I1, and we're just going to linearly interpolate between them to get samples at different values at time t, it, right? And so this is going to bridge a sample from I0 and linearly interpolate to a sample from I1. And since this is a random quantity, for every t, I'm going to let pt denote the law or the distribution of the interpolant at time t. Now, what is the goal of generative modeling? Well, what we want to do is we want to construct some transport that I'm going to model as an ODE that I'm going to initialize at the Gaussian P0 and then transport it using my drift BT such that at time one, my data sample, such that at time one, my ODE sample X1 is distributed as P1. And I'm actually going to ask for something a little bit more. I'm going to say at all times t, right, my xt is random because of my random initial condition. And I'm going to ask that the distribution part of x the
No.
same
Can someone write in the chat if this is my connection or Peter's connection?
satisfies this, right? And so the answer is we just do flow matching, right? If you take bt of x to be the conditional expectation of the interpolance time derivative, so that's just the expectation of my data sample minus my noise sample, I0, condition on my intermediate value, it being equal to x, then this bt of x is going to satisfy exactly that. So if I use this bt of x to integrate my ODE starting at P0, the Gaussian, I'm going to get terminal data samples distributed as P1, right? And so now, how do we learn this drift? Well, we're just going to parameterize a neural network BT hat and minimize the following L2 objective. I'm just going to sample, I0, I1, construct my interpolant, IT, construct the time derivative, which is just I1 minus I0, I regress, and by properties of minimizing L2 objectives, my BT hat is going to learn exactly this conditional expectation. So if I do this flow matching procedure, right, I've learned to drift BT of x such that if I integrate the ODE, I have terminal samples from the data distribution. Now, I see there are questions. Oh,
I'll moderate, don't worry. Good, so we're just chatting out some connection issues, but all is good now again.
okay, perfect. Okay, so now in practice, right, once we have our drift BT, if we want to use it during inference time, we have to numerically simulate the ODE, right? So we want to get our terminal endpoint x1 starting at x0. We have to integrate this drift along the ODE trajectory. And this is going to mean a lot of repeated applications of the neural drift, which is going to be expensive. And so recently, there's been this push over the last year or two for these new models, sort of consistency models and flow maps, which basically aim to bypass this iterative simulation of ODE trajectories and instead try to simulate them in sort of a few or one steps. So concretely, I'm going to define my flow map corresponding to that ODE as a map that takes in 2 times and an x variable. And basically, if I have an ODE trajectory, xt, what it's going to give me is that if I plug in the value of the ODE trajectory at time s, then it's going to allow me to jump straight from time s to time u along that ODE trajectory. And this means that instead of having to, infinitesimally simulate this ODE by evaluating the drift bt, I can just jump between arbitrary time points using my flow map. And in particular, if I take s to be 0 and u to be 1, then it's going to jump straight from an x0 sample, so just a noise Gaussian sample, straight to the x1 sample, the data sample. So I've basically now compressed my entire ODE trajectory into this one-step map that allows me to do really efficient generative modeling. So there are many different ways for training flow maps and consistency models. And actually for our framework, we're a bit agnostic to how you train them. So that's why I'm not going to go into too much detail, but I just want to give you a flavor for how many of the flow maps are being trained. And so basically what we do is we're going to take our flow map and we're going to parameterize it in this residual form, where we start off with the identity function and we add on this corrective residual factor. And VSU here is going to represent what is the average velocity of my trajectory if I start at x at time s and I go to time u. And so now we're just going to parameterize V with a neural network and try to learn what the correct V hat is and the induced flow map x hat. And so we're going to use 2 loss terms. And the first one is what we call the diagonal loss, which is when s is equal to u. Right? So VSU is the average velocity along a trajectory. So if you take the limit as s approaches you when s is equal to u, this should just give you the instantaneous drift, right? The instantaneous drift of the ODE, which was just our BU of x from before. And so if we want to ensure that my VUU is equal to BU, right, we can just do the flow matching just as before, right? And if we do the flow matching loss, right, and we minimize this, well, then on the diagonal, VUU of x will equal exactly my drift BU of x. So this diagonal loss just ensures that my average velocity is correct when s is equal to u, and it equals the instantaneous drift BU of x. And then we need a second loss, right? So if we have the correct instantaneous drift, we need to ensure that for s not equal to u, that my average velocity is actually the real average velocity, which will guarantee that x is actually a valid flow map. And there are many different ways of enforcing this consistency loss. So a few losses include like the mean flow loss, shortcut, Eulerian, Lagrangian, terminal velocity matching. But I'm just going to present this really simple one based on the semigroup property. Because at the end of the day, any consistency loss has to guarantee that this property is satisfied. And what the semigroup property just says is that if I start at a value x at time s, and if I jump to some intermediate time w, and then from w, I jump to time u, that's the same as if I started at s and jumped straight to u, right? Integrating the ODE trajectory from s to w, and then from w to u should be the same as integrating it straight from s to u. And you can show that if you satisfy the semigroup property along with the previous diagonal condition, then you have a valid flow map. So how do we enforce the semigroup property? Well, we could just use a really simple loss that for concreteness, I'll write down here. And basically it just says, I want this property to be satisfied. So let me just penalize violations of this rule. Let me just take the left side, subtract off the right side, and try to minimize this, right? And the minimizer of this loss is going to give you a loss of 0. And when it's 0, the left, this term is equal to 0, which means exactly that the left side is equal to the right side. And so then we have the semigroup property. And so basically training these flow maps is just going to be 2 losses. You're going to train the diagonal using flow matching, and then you're going to train the off diagonal with this sort of consistency loss. Okay. So at the end of the day, what we have now is that we have some drift BT such that if we simulate ODE trajectory starting at P0, we end up at P1. And on top of that, we've now learned to flow map right? Which instead of having to, infinitesimally simulate the ODE dynamics and take lots of Euler steps, allows us to jump straight from time 0, straight from a Gaussian sample to a data sample at time 1 in one step, right? And so in particular, my flow map, if I fix the S and U to be 0 and 1, then it's going to push forward the Gaussian distribution to the data distribution, right? Evaluating my map on a Gaussian sample gives me a sample from the data distribution. But importantly, it's going to transport P0 to a single distribution P1. So let's think of a really slight extension of this idea of flow maps to something let's call context-dependent flow maps, where instead of trying to target a single distribution P1, let's say that I'm actually trying to target a family of distributions, which I'm just going to index by some variable C. So I have some collection of contexts C and some larger set C, and I have some distributions PC, and I want to be able to sample from either of these distributions. Well, a really easy thing that we could do is we could just say, let's let our flow map take in this additional input, C, the context or conditioning value. And once we fix the C, then it's going to act like a flow map transporting P0 to that fixed distribution PC. And if I change the C here, then my target distribution will change. But in each case, for a fixed C, it's just a usual flow map. And we're actually already really familiar with this idea if you consider class conditional generation. So for example, imagine that P1 is the distribution of all images or something like that, all ImageNet images. And oftentimes we don't just want to generate an image of any of the images. We want to generate from a specific class, such as a cat or a dog or a hamburger. So what do? We usually let our neural network, our flow matching model or a flow map, take in the class index C for which class. And then once we put that class index into our neural network, it's going to transport the Gaussian distribution to that specific subset of the distribution. So specifically, it's going to give us samples of cats or specifically samples of dogs. Right? And so for meta flow maps, we're going to be training exactly those context-dependent flow maps, except I'm going to choose a really specific context set and a really specific collection of those distributions. And in a few minutes, I'm going to explain why we choose them, and it's going to be for that reward alignment goal. But let me just now explain an overview of what meta flow maps are. So first, what is the context? The context that we see from before are just going to be time state pairs. So I'm going to let T be any time in 0, 1, and X just be any variable in RD, any vector in RD. And so now what is my PC? What is that distribution that if I fix the T and X, I should be targeting? It's just going to be the law or the distribution of I1 conditioned on IT being equal to X. And I'm just going to denote this with the notation P1 given T given X. So just intuitively in words, what is this saying? Well, it's saying what is the distribution of the clean sample, the clean data sample I1, given the noisy observation IT is equal to X. So if I fix the T and I fix the noisy sample X, I want to be able to sample from the clean distribution of data samples. So let's just maybe visualize this quickly with this visualization. So let's say that P1 is this distribution of images, ImageNet images. And then here I have P0 as my Gaussian. Let's say that I observed this noisy image. We don't know exactly what the true data sample is that corresponds to this noisy image, but there is some distribution of images that it could have come from, right? So clearly, this is a noisy dog. So clearly it should be a dog that was the clean data sample, but we don't know exactly which one it was, right? There's some distribution and not just a point mass over here that it could have come from. And so if I plug in this T and this X, so the noisy dog into my meta flow map, I now want to be able to generate arbitrarily many samples from this posterior distribution of what is the clean dog that arose from this noisy dog. And so if I fix the T and X in my meta flow map, it's going to exactly transport the Gaussian prior distribution to this specific posterior distribution. On the other hand, let's say that I observed a noisy image like this one. Clearly, it's a noisy flower, right? So the posterior distribution of what was the clean flower, right, that gave rise to it, what was the clean image, right, is going to be something, let's say, like this distribution here. And so if I plug in this other conditioning information, so this new T and X here, like the noisy flower, into my meta flow map, I now wanted to transport the Gaussian distribution to this other posterior distribution, right? So if I let my first input be like, let's say epsilon, so this is going to be my prior sample from the Gaussian, notice that if I plug in the exact same epsilon, so the exact same noise sample, if I have my context information as the noisy dog, this sample is going to be transported to a clean dog, a sample from that posterior. Oh, yeah.
Yeah. Why do you call this meta flow maps? Like we just have a conditional model now, a class conditional model.
Yeah, completely. Essentially, what it is that you have a collection of flow maps, right? And what's meta about it is that you're just selecting from this infinite collection of flow maps by specifying what the context information is.
Um, yeah, so and you're doing that by having a conditional model. So
Yes. Yeah.
we yeah, we don't have to think of anything meta or anything what it now means to have your thing to be um yeah, class conditional or so. We just have now our one, or we can just think of the single scenario of the dogs, and then whenever we want something, yeah, and then of course we can also have this additional class input, and then we it extends to the case where it's conditional, where it's meta, if you want to call it that.
Sorry. So one thing I should be clear is that the context information is purely from this sort of like self-referential process, right? So we have some process which takes like the Gaussian distribution P0 to the data distribution P1. And so
Yeah.
I'm not really saying, I'm not trying to call all of these context dependent flow maps. So like for me, with context dependent flow map, what I meant here is you could put any conditioning information, such as the class or anything here, right? And it's going to sample a new distribution. For us,
Mm.
what we're considering, why we're sort of considering a really, really restricted subclass of this, like,
Yeah.
global framework where you can put in T and X coming from the sort of sub process that you're considering, right? So you have an interpolant process transporting you from I0 to I1. And you're going to be able to put any of the sort of intermediate values of your process, right? Like, so if you were simulating ODE trajectories, you're going to put in intermediate values of these ODE trajectories back into your map. And then conditioned on sort of like, the intermediate value of this flow, you're then going to be targeting a new distribution.
Okay,
Sort of.
okay, sorry. So it's not class conditional, it is yeah, you condition on this noisy sample here next to your noise.
Exactly, yeah. So sorry, when I was saying that we put in this noisy dog into my meta flow map, you shouldn't be thinking dog. The neural network has no notion that it's a dog. All
Yeah,
you're
of course.
feeding in.
So we are feeding, it's clear now, I think, to
Okay.
everyone, including me. I'm just the slowest one, probably.
No, no, yeah.
Then you're okay. So you now, we will get to your training process soon, I believe. Yeah,
Yeah,
sounds good.
perfect. Yeah. So perfect. So just to recap this, I'm going to feed in this noisy image, whatever it is, into my meta flow map as this X input here. And then I'm going to take some Gaussian sample here, such as, let's say, this epsilon. And if I take two different epsilons, right, epsilon prime versus epsilon, but keep the noisy sample here fixed, I'm going to get two different samples of clean data, right? Two different possible reconstructions of this noisy dog. On the other hand, if I keep the noise fixed, so the first input fixed at epsilon, but if I vary the conditioning information, which for us is not going to be class, it's going to be, this noisy image versus this noisy image, then I'm going to take the same prior Gaussian sample epsilon to two different reconstructed images, right? Reconstruction of what is the clean sample for this noisy image, and then the reconstruction of what is the clean sample for this noisy image. Okay. And so as a really quick overview, I'm going to spend the next 10 minutes talking about a reward alignment. Then I'm going to come back to describing meta flow maps and how we actually train them. And then finally, I'll put them all together and explain how we can use meta flow maps for reward alignment. But just to visualize it one more time, just so that we're all on the same page. So in the first columns here, what we have are true ImageNet images. right? They're going to be the same ones in the two subfigures. And then in the second column, we have noisy observations of the first column. And this is in latent space, so that's why it looks a bit weird, right? But importantly here, you sort of have a very high noise level where it's really difficult to see what the original image is here. Whereas in this case, you have a much smaller noise level. And so you can see that, you're better able to see what the original image is. And then in the next four columns, we're just sampling using our trained meta flow map of what is the clean reconstruction given this is the noisy sample. And so you can see over here, when you're at this high noise level, right? The images are, closely related to each other, but there's some variation, right? So for example, in this case, right, clearly there's a lot of difference in colors between the four reconstructions. On the other hand, for this smaller noise level, right, we see that all the images are much more similar to each other and to the original image because these posterior distributions of what the clean image is are going to be much tighter and much more concentrated around the true original image. Okay, so now let's come to the problem that we're interested in, reward alignment. So we had our pre-trained flow or flow matching model, right, that samples from the data distribution P1, and we have some reward function R of X. And this reward can be arbitrary, right? It could be a likelihood, it could come from, an inverse problem, it could be a black box neural network that, measures, are images pretty or do they adhere to captions, whatever you want. And our goal is instead of sampling from the data distribution like our original model did, we want to sample from this reward tilted distribution, right? Areas where there's high density under the data distribution, but also areas where the reward function scores highly, right? And so we just formalize this as trying to sample from P reward of X, proportional to this distribution. And so there are sort of two paradigms for alignment that you could consider. One is you want to do this at inference time. So this means that we're going to keep our drift B fixed, our flow matching model fixed, and instead you're just going to try to modify the sampling dynamics, right, so that you target this new distribution P reward. And importantly, this is often really expensive. You either have to do lots of trajectory rollouts or you need huge particle ensembles if you're trying to do SNC. The other approach is fine-tuning. And here is where you take your drift BT and you're actually going to try to permanently update the model parameters so that it targets P reward, this reward tilted distribution, instead of the original data distribution that it target. But importantly, because you're trying to update the entire model, right? Maybe you can use LoRa, but in general, this is going to be quite expensive. And so doing it for every downstream reward is often not feasible. Now, despite sort of the operational differences between those two paradigms, the mathematical solution is actually the same in both cases, right? So we had a drift BT that took us from P0 to P1. Now we're going to search for an ODE with drift BT star, where the star is sort of going to denote that it's like the optimally tilted drift, such that if we use the drift BT star and we take samples from the prior distribution P0, it's going to now transport us to samples from the tilted distribution P reward instead of the data distribution P1. And so the question is, what is this optimal vector field BT star that we want? And so the optimal vector field BT star that we want can be expressed in terms of the value function of the interpolant. So intuitively, the value function is just telling us what is the expected future reward given the current state. So I'm going to define VT of X to be the log expectation of the reward of the clean data sample I1, given that the noisy observation IT is equal to X. And I'm just going to rewrite it here. Again, it's this expectation of the reward of X1, but now I'm just going to indicate here that X1 is sampled from this posterior distribution, right? This exact distribution here, the distribution of the clean sample I1, given IT is equal to X. And, just hinting at what we're going to do later, right? X1 from this distribution is exactly the distribution that our meta flow map is going to allow us to sample from. So if we've defined this value function in this way, then you can show that the optimal dynamics, the optimal drift BT star to sample from the reward tilted distribution is going to be your original drift BT of X plus some scalar coefficient, and then the gradient of the value function. Now, if you're interested in how we get this ODE, I'd be happy to talk about it later. It's sort of well known in the literature and it's related to Duke's H transform, but its exact form isn't that important. All that you should really take from this slide is that it's the original drift BT of X, which we assume you already have, and then this gradient of the value function, which intuitively is just going to point us in directions of high expected future reward. And since we already have BT of X, our goal is going to be in inference time steering, how can we approximate the gradient of the value function? Because if we can approximate it, well, then we have this entire drift, so we can integrate it. And in the case of fine tuning, how can we set up a tractable objective to actually learn this entire quantity? So how can we go about estimating that gradient of the value function, right? That's the term that we really need to estimate if we want to do efficient inference time steering. So I'm just going to rewrite the definition here of the gradient of the value function. So this is my value function. I just copied it down from the previous slide. And then I'm going to take its gradient, and I'm just making clear that it's the gradient with respect to the X input, right? So it's a gradient with respect to this distribution here. Now, what's the trick that we love to do in machine learning if we have the gradient with respect to some distribution that we're sampling from? Well, we're just going to do a reparametrization trick. So let me find some generative map phi, which takes in epsilon t and x, and it's going to take some noise distribution q. And by the way, q is just going to be p0 later. I just wrote it a bit more generally or abstractly here. And if I fix this t and x here, the second two inputs, then as a function of my first input, as a function of this noise sample from Q, it's going to give me a sample exactly from this posterior distribution, right? So I'm just reparametrizing this family of posterior distributions, right, through some generative map phi. So if we have this reparametrization, then I can just rewrite the value function as the expectation under the noise distribution Q, and then the reward of my samples from this posterior distribution, right? This is just the reparametrization trick. And now, right, if we're going to want to be able to differentiate this quantity with respect to X, because that's what we want for the gradient of the value function, then it's quite natural that we're going to need our phi to also be differentiable with respect to X, right? Eventually, that's going to allow us to exchange the order of the expectation with the gradient.
So
Yeah.
and this is now where the niceness comes in of your map being able to be conditioned on an intermediate noisy sample, because then or this implies that you no longer have these like incorrect bad estimators as we would have with a diffusion model where we predict the expectation of x given xt. Here you instead you sample a clean x1 given xt, and then you sample a bunch of these, and then you get like a kind of good estimation and not a wrong estimation. Or in the limit, you actually would get a correct estimation of your value function. Is that true?
Exactly. Yeah, perfect. I couldn't have said it better myself. Yeah, exactly. So
Okay.
just to repeat that, oftentimes what people will do is instead of taking a sample from this posterior distribution, we're just going to approximate it with a point mass at the the mean, right? The denoised mean. And we're just going to take the denoiser and just estimate it, at the denoised mean. Whereas instead, what we're saying here is let's actually be able to sample from this full posterior distribution. And if we can sample samples from this posterior distribution, then we're going to get a good estimate of the gradient of the value function.
Wait a
So
second, Peter. What we're
yeah.
saying here is missing one ingredient. Why, if I have a normal diffusion model, why can't I do the thing of just sampling my ground truth thingies and then, or that is of just sampling my distribution conditioned on XT?
So if you want to obtain samples from this posterior, you are correct. You could roll out these SDE
Exactly.
trajectories from time t to one, but one that's going to be expensive, right?
Yep.
Many steps, but even worse, we actually need the gradient. So if you want the gradient and not just posterior samples, you have to differentiate with respect to your starting point X. And differentiating through these entire SDE rollouts, that's just not tractable at all. So
Yeah,
you could obtain those.
we need a gradient if we do this gradient type guidance.
Yes.
But
Yeah.
if we want to do like some particle method that we've seen oftentimes now as well, then that would also work without a gradient. On that note, actually, maybe it's the right time to discuss. What's your feeling right now of how much better some gradient-based methods work compared to like some particle-based methods that then don't need a gradient?
So my hunch is that when you do have access to gradients, if you can get good estimates of the gradient of the value function, you're going to do much, much better than particle-based methods. The issue is that getting good estimates of the gradient of the value function has in general been very difficult. And most people have to rely on sort of like these coarse approximations, such as like approximating the posterior with a point mass at the denoised mean. But if you were able to get good estimates, which I hope, like sort of, I'm going to try to convince you metaflow maps lets you to, then you're going to do much better than sort of SMC or any of these particle-based methods.
Okay.
All right, perfect. So just to repeat what was said, if we do have such a map phi, right, how can we get consistent Monte Carlo estimators of the gradient of the value function? All we're just going to do is that we're going to sample a batch of noise samples from Q, right, from our Gaussian distribution. We're going to push forward them in one step with our map phi to get samples from these posterior distributions. So now I have this collection of posterior samples. I just estimate the value function with this log sum exp. And then since I'm assuming that my map phi is differentiable with respect to x, right? That was the second requirement on the previous slide. I can now differentiate this quantity with respect to x, and I now have a consistent Monte Carlo estimator of the gradient of the value function. And so, there's sort of two things that we required here, this reparametrization, right? This conditional transport constraint that I transport Gaussian samples Q to posterior samples. And then the second one was that my map phi was differentiable with respect to x. And the question now is, how do you train such a map? And so I'm just going to say that there actually have been some previous works that have explored how you can sort of learn maps like this. However, many of them use methods such as MMD for training, which are in general quite difficult to scale and tune. And so we instead borrowed on ideas from like flow maps and flow matching, which are oftentimes more scalable in order to learn such maps phi. And for us, the answer is exactly train a metaflow map. Okay, so that was reward alignment. Now let me go how we're actually going to train those maps phi that are going to give us good estimates of the gradient of the value function. So the construction works as follows. First, for each context Tx, right? Each context Tx, the noisy sample x, gives us some posterior distribution of what the clean reconstruction is. And for each of these, we're going to construct a theoretical ODE that transports the prior P0 to that specific posterior, right? And this ODE is just going to be nothing but conditional flow matching, right? If you took samples from P0 and samples from this posterior and did flow matching, right, you would get some ODE that transports you from P0 to that posterior distribution. So we have an infinite collection of posterior distributions and an infinite collection of conditional ODEs. And for each of these auxiliary ODEs, it has some associated flow map, right? That sort of learns its solution operator, that compresses its trajectories, so you don't have to simulate the infinitesimal ODE, but you can instead jump from in one step from the noise sample P0 straight to a sample from that posterior. And instead of training all of these infinite, networks separately, of course, nobody would do that. We're just going to train it all under one infinite collection, all under one model simultaneously. And we're going to call that a metaflow map. So let me just go into a bit more detail. So first, let's define that conditional auxiliary ODE. So we're going to have some ODE that I'm going to denote with x bar s. And the reason that I'm putting the bar here is just because I want to be clear that unlike before, where we just had the previous ODE, here it depends on some context information Tx that we're going to hold fixed. So T and X is fixed. We have some drift B bar, right, which is a function of our ODE variable x bar s, where T and X are fixed. And we want to choose this conditional drift B bar so that if we initialize at the Gaussian P0, then we're going to end up with a terminal data sample from the posterior distribution. So how do we choose this conditional drift B bar S? Well, we can just do flow matching again from the prior, but now instead of doing a data sample from P1, we're just going to replace it with a sample from the posterior that we're interested in, right? So we're going to construct our new interpolant I0 bar, which is still a Gaussian sample, and then I1 bar here, but I1 bar is now a sample from this posterior. And so if you just do conditional flow matching, right, keep T and X fixed, and just look at the expected conditional velocity, then you're going to exactly learn a drift B bar S, which transports you from P0 to this posterior distribution. Now, each of those conditional ODEs, right, fixing T and X, has some flow map. And so we're just going to propose that you learn all of them under one model, which we call the meta flow map. And so our meta flow map is going to have 5 inputs now. It's going to have the context information T and X, right? So this is your noisy image, and this is the time at which you observed your noisy image. And once you fix T and X, you're just going to have a standard flow map as a function of the first 3 inputs, right? That for the conditional trajectory is going to jump from time S to time U of that conditional trajectory. So I just want to be clear that the S and U are unrelated to T. T is just telling me when did I observe my noisy sample, but then the S and U are sort of these inner flow times that are saying, if I want a sample from the posterior distribution given these 2 inputs, then sort of like this is parametrizing the flow from time S to U of exactly that transport.
Would you say that we're then also training something useless here or spending some useless time where the T could be larger than both S and U?
So yeah, that's so crucially, T and S and U shouldn't have any relationship. So like when T is larger than S and U, there is still some posterior distribution, right, that you might want to sample from. And so you would still want a flow that goes from time 0 to time 1 to sample from that posterior
But that
distribution.
will
I
never this you will never encounter this in your reward guidance. So why spend training time there?
uh you will encounter it actually.
Oh yeah, right. You encounter it at the very beginning.
Yeah, so you definitely will encounter it, but I completely agree that for different T, the challenge of the problem, like the posterior distribution is
Yeah.
going to be sort of really easy or really difficult to learn. So you might want to spend more or less time training there. So that's definitely something we explored. But in theory, you should train over all T, S, and
Yeah.
U. Yeah, perfect. Okay.
Nice.
So let me just quickly come back to this diagram, just quickly one more time as an overview. So we had this noisy image. It induces some posterior distribution of what the clean image is. If I put T and X into my meta flow map, I have these conditional ODE trajectories that I'm indicating with these red lines or these red curves, right, that transport the prior P0 to that posterior distribution. On the other hand, if I input this noisy image here, right, I have a new posterior distribution. And so I would have a different ODE as indicated by all these green curves that would take me from P0 to this posterior distribution, right? All of these guys are the individual ODE trajectories. And a meta flow map is just saying, let's just learn the one-step maps directly from the starting point to the endpoint for all of these conditional ODE trajectories. So how do we train them? So it's actually just as easy as training a regular flow map. What you're going to do is you're going to sample a T and an X. So you're just going to sample a noisy image X at some time T. You're going to put it into your network. And the realization is that once you fix T and X, the resulting subnetwork that you have should just be a standard flow map for that specific posterior distribution, which means that you can just train it like you would with any flow map for that specific posterior. So once again, we're going to parameterize in residual form. We have our identity, we have a residual term. V bar SU is now the average velocity for the conditional trajectory. And we have 2 losses, the diagonal loss, which is going to ensure that the diagonal is correct, so that V hat SES is equal to the true conditional drift B bar S, and then an off diagonal loss that enforces the consistency property. So let me just quickly go over that in a bit more detail. So we're going to consider what happens when we're just trying to train from data. So first, the diagonal loss. And we're going to do this by a construction using 2 coupled interpolants. So first, how do we sample the context information? So that xt that we had before. You're just going to construct this as you would with any interpolant. You're going to sample an I0 from the prior distribution, from the Gaussian, and you're going to sample an I1 data sample. And then you're just going to construct the interpolant to get IT. So this is going to be my context information. That's just the same as before. But now, when you're trying to construct your conditional auxiliary path for your conditional flow matching task, you're going to sample an independent I0 bar. So these I0s are independent from each other, but you're going to use the same data sample I1. Okay, so the I0 bar and I0 are independent prior samples, but I1 is the exact same one. And the reason for this is, let's look at what happens conditioned on the context information. So conditioned on IT being equal to X, what is the distribution of I0 bar and what is the distribution of I1? Well, the distribution of I1 conditioned on IT being equal to X is exactly a sample from the posterior distribution, right? That's sort of just the definition of the posterior. If I observe IT is equal to X, what is the distribution of I1? And then since I0 bar is completely independent from I0 and I1, it's again just going to be distributed as P0. So what I'm saying here is that condition on my context information being equal to X, the distribution of I0 bar is the Gaussian sample P0, and I1 is exactly from the posterior sample, which means that this conditional auxiliary path gives us the exact supervision we need to train the diagonal, right? If I do flow matching with this path here, right, where its time derivative is I1 minus I0 bar, if I feed in the IS bar interpolant into my network, and if I fix the context information TX, then the minimizer of this loss is exactly going to give me that conditional drift B bar S that I was looking for. Okay, so this is just a collection of conditional flow matching tasks where I'm going to condition on this coupled interpolant. And so, just importantly, if we minimize that loss, the important part is that our diagonal is going to be correct. We're going to have the correct instantaneous auxiliary drift B bar U with the correct context information TX there. And so now we just need a consistency loss that guarantees that if I hold T and X fixed, that as a function of the other three inputs, I have a valid flow map. And this is again just saying fix T and X, enforce the semi-group property on the first three inputs, right? Just as we had before. So again, there are many different losses you could use, and we even explored some of them in our paper. So we used mean flows, Eulerian, Lagrangian, a bunch of different ones. But I'll just present for concreteness this semi-group loss, which is going to say I'll sample T and X, and I'm going to hold them fixed, right? So T and X are going to be fixed everywhere. Let me just penalize the residual of the semi-group property, where I want to say if I'm at some X bar at time S, and I jump to time W, and if I then take that value and jump from time W to U, it should be the same as jumping from S to U. And I just penalize this difference. And again, if I minimize this loss, I'm going to have a loss of 0, which means that holding T and X fixed, I exactly have the semi-group condition, which would mean that for every T and X, I have a valid flow map, right? And coupled with this, diagonal condition that I have the correct instantaneous drift, that would mean for every T and X, I have the true conditional flow map. And so I've learned a meta flow map. So just to say this again, basically the high level idea is sample a T and X. And once you fix those in your network, train it as you would any standard flow map. Now, so far we presented how we train this from data. So this is where we don't assume we have a pre-trained network or anything like that. And I've been presenting this all for the case of a Gaussian interpolant where P0 is Gaussian. But it's actually much more general than that. P0 doesn't have to be Gaussian, and you don't even just have to consider interpolant processes. But that's our main setting, so that's why I presented it this way. But now I'm going to present how you could actually do distillation from a teacher drift BT. But now we're definitely going to require that P0 is Gaussian and that we're in this interpolant framework. And it's going to use a really cool result called glass flows by Peter Holdrive. And I'm pretty sure you guys are familiar with Peter. And basically what this result says is that if I want this conditional drift B bar S, then if I already have a pre-trained unconditional drift BT from my original ODE, then I can analytically compute what this drift B bar S is as a linear combination of X bar, X, and then my drift B evaluated at some new point. The exact expression here doesn't matter too much. All that matters is that if I have my unconditional drift B, then I actually can analytically evaluate what my conditional drift B bar S is. And importantly, this means that in my diagonal loss, right, instead of doing the conditional flow matching as I did before with coupled interpolants, I can just regress against this teacher drift B bar S, right? Again, this is only in the case where I already have my teacher available B. And the benefit of this, of course, is that you don't have to do flow matching, right? You have zero variance targets. The minimizer is perfectly zero. So it's going to be a bit more stable if you already have a pre-trained teacher. And there are also tricks you can do for the diagonal, the off-diagonal loss, the consistency loss to make it more stable, but that's not too important. Okay, let's see here.
Conditional here means conditioned on a noisy sample, not conditioned on, for
Yes.
example, a prompt, right?
Yes, sorry, yes. So in this talk, whenever I say conditional, I'm always going to mean conditioned on the noisy sample X. Sorry, I should have been more clear about that. You can, of course, add in more context, right? So instead of just training a meta flow map X that takes in the context information, you could also allow it to take in a prompt. So for example, on ImageNet, we actually also allow it to take in the class index. So, you could add more context, but just in the presentation, as I've had it here, I'm going to mean that it's conditioned on like this context TX, the noisy sample. Exactly. Do you need the original data for distillation? So no, you don't, because, oops, sorry. Let me come back here. So this is actually going to become a pin style loss, right? If you want to minimize this loss, you just have to sample over all X bars, T's, and X's, which means that you don't actually have to sample from the data distribution. And same thing with the consistency loss. So you could actually sample from any distribution in theory, and you would be able to minimize this, and then you would have a valid meta flow map. Of course, in practice, right, the closer the distribution you sample from is to the distribution that you're interested in, the results are going to be better. So it would be good if you had data or if you could simulate using your drift B. But in theory, this loss does not require you to have access to the data distribution. You could sample from any distribution, the X bars and X's, and the strict minimizer will be the true metaflow map. Okay, so I'm going to go over this a bit quickly. How do we do inference time steering with metaflow maps? So remember, our goal was to sample from this reward tilted distribution, P1 of X, and then biased in areas of high reward R of X. The optimal drift was the original drift BT of X plus this corrective factor coming from the gradient of the value function. Now, this unconditional drift B, we assume you already have. Either you've already trained a model BT, or you can actually extract it from a meta flow map. And so in all of our experiments, we actually extracted directly from the meta flow map, but I won't go into that. What I just want to quickly explain is, once again, how we can estimate this term, because that's really what the meta flow map is going to allow you to do. And we're just going to plug it into the exact same estimator we had before, except I'm going to replace phi with my meta flow map going from time 0 to 1. So I sample a batch of samples from the prior distribution P0. I push them forward in one step to posterior samples from the posterior conditioned on this noisy observation, log some X to get an estimate of the value function, and then I just take the gradient. And so at each step, right, when I'm trying to integrate the Doob ODE, I'm going to do this. I'm going to estimate the gradient of the value function. And now I have an estimate of my drift. And I'm just going to use this in my drift for the ODE. Okay. We also explore fine tuning. I won't go into the details because I'm running out of time. But a naive thing would just be to regress onto this estimate. But even though this estimate is good, it's biased for any finite n. And so if you just tried to naively regress onto this, you would have a biased fine-tuning objective. So we actually figured out a way, we actually came up with a new objective that is completely unbiased, but still uses sort of this metaflow map framework. And it's unbiased and it's off policy, but I'll just leave that for another time. So I'm going to come into the experiments now quickly. And so we definitely explored lower dimensional experiments like Gaussian mixture models where, we can measure KL and MMD and all these different values, but I'll just focus on ImageNet experiments for now. So our main experiments were on ImageNet 256 by 256 in latent space, and we took an SIT model. And so the first thing to note is that you have to adapt the SIT model a bit, right? Standard diffusion transformers just take in two inputs, right? A time and an X. Whereas our meta flow map needs 5 inputs, 2 X values and 3 time inputs. So you have to update the architecture a little bit. But we tried to stay as faithful as we could to the original architecture. And so we actually took the original architecture, which was 675 million parameters, and only added on an additional 8 million parameters. So by taking on these additional 3 inputs, you only increase the parameter count by 1.3%. So it's quite minimal. And so in the paper, we explore how do you results where we train both from data and from distillation. And for data, I'll just refer you to the paper. But then for like the state-of-the-art results, we tried to just use a pre-trained flow map that was already really good and just fine-tune it into a meta flow map. And our motivation here is that actually training the meta flow map on top of a flow map is really easy. You just add on a few parameters and do a few extra steps, and it's really easy to adapt it into a meta flow map. And just to give you a rough comparison of the compute cost, so the pre-trained checkpoint that we took, the original flow matching model was trained on 800 epochs of the data set. Then the flow map was fine-tuned into like from a flow matching model into a flow map with an additional 80 epochs. And then we took an additional 30 epochs to take it from a flow map into a meta flow map. So, compared to the 880 epochs, 30 epochs is really small. Now, I want to say quickly, just to caveat that one step of training an MFM is going to be a bit more expensive than a step of training the base flow matching model, but it's not that much more expensive. So it's still much, much cheaper. Okay. So here we can also do unconditional sampling with the meta flow map. Now, you probably wouldn't want to do this. There's no point to. Just use your standard flow map. But we just wanted to show that even by giving you all of this access to all these extra posterior sampling capabilities, that we still could get pretty respectable FID scores with our meta flow map. So in 4 steps, we were still able to get a sub 2 FID. Oh, yeah.
Does it deteriorate quality? Yeah, I guess a bit. Right. All this additional conditional training deteriorates
Yes,
unconditional generation quality.
definitely. Yeah. Your meta flow map, instead of just learning to sample from one distribution, is now trying to learn to sample from like this infinite collection of distributions, right? Condition on every T and X. So it's definitely going to deteriorate a bit. But we still got somewhat respectable FIDs, I think. Okay.
Then maybe this is a good moment to ask about diamond maps. Do you know that paper?
Yes. Yep.
And in their scenario, is it the same case that there's some because this degradation of quality might hint at the fact that not all niceties are preserved, not all a nice generation capability of the model is preserved with this additional training. And then in diamond maps, that has a different strategy. Is it different there that they are able
So they're
to?
actually doing the same thing.
Okay.
So yeah,
So
so
then
if you
maybe you
guys see,
can put us a bit more context.
so sorry, diamond maps, I need to review the paper, but I believe basically they considered this. So it's also a paper by Peter. And so they consider exactly this distillation framework where you have the unconditional drift BT, and you want to basically, so what we call a meta flow map, they call a diamond flow. And so they exactly try to distill this B bar S onto the diagonal. So I think that like the distillation framework here is exactly what diamond flows does. So basically they're very, very similar.
Okay, the Peters are doing the same stuff.
Yep. And we're now collaborating on some follow-up work together. So we'll just unify instead of going separately. So let's see here. Okay, so I'm not going to go into the details, but we took these experiments actually from glass flows, and we just wanted to ensure that we really are sampling the posteriors well. So we have a few different evaluation metrics, and it sort of does show that we beat out glass, especially in this low floating point regime. But just for time, I'll leave that for later. And instead, I want to focus on our inference time steering, because that's sort of the main pitch that we have. And so in this experiment that I'm going to show here, let's say we have a specific class condition ODE targeting a class tabby cat. And we're going to have 3 separate experiments where we want to steer towards high reward regions on image reward, pick score, and HPS. And for those of you that aren't familiar, these are all models that are going to take in an image and a prompt, which for us is a high quality, high resolution photograph of a tabby cat. And basically, it just gives high score if the image and the prompt adhere to each other and if the image looks good according to like some
Yeah.
perceptual qualities. And so what we do is we are just trying to steer into high areas of this reward. And so here are the results. And so the first curve that I want to emphasize is this black curve. And basically all this black curve is a best of n sampler. So you're just going to roll out a bunch of trajectories and then take the best of those trajectories. The top curves here are going to be from exactly the procedure that I was describing before. You're going to simulate the Doob ODE, and at each step, you're going to take some number of Monte Carlo samples using the meta flow map in order to estimate the gradient of the value function. And so like the first point here is we take one Monte Carlo sample, then two, then four, then eight, then 16, then 32. And I want to show you that even this first point, so even when you estimate the posterior with a single estimate to get the gradient of the value function, you're already beating this baseline best of 100 sampler, and you're doing over 100 times fewer compute. Sorry, best of 1000 sampler, and you're doing over 100 times fewer compute. So I think this sort of is really showing that, you know, using these sort of particle-based methods where you're exploring, right, might not be as performant as sort of using something where you are able to estimate the gradient. Another curve that I want to show you here. So in the case where you don't have a differentiable reward or where you just don't want to be taking gradients, we explored a few different ways of doing that. So one way is you can actually get an estimate of the gradient of the value function for non-differentiable rewards. But we found to be more performant is a variant of Monte Carlo tree search, where instead of estimating the value function with trajectory rollouts, you just use our meta flow map to estimate the value function. And so once again, you can see that like these are sort of these diamond points that we're able to outperform best of n here as well. And so these are using no reward gradients. Okay, and here I just want to visualize some samples. So in the first column here, we have our base meta flow map. In the second column, we have our steering procedure where we're steering on, I believe this is HPS. And here we're just using one Monte Carlo sample to estimate the posterior. And then in the final column, you are using 32 samples to estimate the posterior. And I sort of think that there's this nice progression from left to right. And then, okay, I'm running out of time, but I just want to say we also explore for fine tuning. So here we fine tune over, you know, all of the classes on HPS, and we sort of monitor how HPS reward does. We also monitor pick score and image reward just to make sure we're not reward hacking, right? So we only train on HPS, but we monitor all these rewards, and we can see that we sort of, you know, have a nice improvement. And then here are some generated samples. These are separate runs, just we're increasing the strength of the reward signal. And you can see that as you increase the reward signal, you know, you get sort of more fidelity to the actual reward. Eventually it'll become oversaturated, but that's sort of expected. So yeah, that was an overview of meta flow maps. I guess now I'll just leave over this overview slide. Are there any questions that you guys have?
I suppose my main point of the diamond map comparison, diamond flows comparison is already cleared up with a simple clarification. But yeah, what are some other questions? I guess let's go with the chat. Are you extending MFM to sampling from unnormalized densities? No data.
So yes, that is something that we're currently looking at. You know, in general, just for where is it? Sorry. This problem, right, of, you know, reward alignment is very closely related to sampling, right? If R of X is like a density that you're interested in sampling from, and, you know, P1 of X is some simple prior, and you just take R of X to be the log density you're interested in minus the log of your prior, then your target distribution is exactly sort of this, you know, unnormalized density. And so you can actually repurpose all of this machinery instead of being for like reward alignment to actually be a neural sampler. So that's something that we're currently trying out. Did you also try out different architectural settings for including conditioning? So did you concat your conditioning, and have you tried out different approaches? So I'll be honest, we haven't ablated the architecture enough yet. We sort of just found the first thing that we tried to be quite easy. But that's definitely something that now that we have more time after submissions, we're trying to figure out sort of the design space of how to train these maps even better. And if you have more questions, Adi is on the call, and he did a lot of the work with actually training them. So he could also have some perspectives if you have more questions there.
Also, Lena, feel free to unmute.
Hi, thank you for the talk. My question might be a little bit naive, but it's related to this something from a normalized target distribution. So you've talked about this reparametrization trick and this map, this flow map, and I'm curious, how do you learn it in the case where you just have energy and no data?
Yeah. So one example would be, let's say that you take P1, let's say that you're interested in some Gibbs distribution, and you just take P1 of X to be that distribution at a temperature for which you could already obtain samples from, right? In that case, it would be easy to just train the map directly to sample from P1 of X. And now you're trying to tilt it to a different temperature. So that's one approach that I think is quite common for, let's say, molecular dynamics. Another one is just to do something like choose a prior like the Gaussian, for example, and then just try to tilt it towards, a difference of the log densities that you're interested in.
I see.
But I agree. In both cases, like P1 of X is either some distribution you assume you can sample from with Monte Carlo samples or some simple prior distribution.
Mm-hmm. Okay, makes sense. Yeah, in the case where it's a simple prior distribution, I guess it's like you might get very like big difference in the log densities. Yeah, but thank you.
Yeah, completely agree. So if P1 of X and your density, if there's a bit of a support mismatch, then the R of X will be really, poorly behaved and can get really, really large or really, really small. And so that definitely could be an issue. So that's why we're going to see if it works. But I would say that in general, that's often an issue with many neural samplers. Whenever you sort of have some prior distribution and R of X and your target is quite far, you'll always have a lot of these issues. But yeah, we definitely have no idea if it'll work or not.
Yeah, makes sense. Thank you.
Okay. Then let's go with this one last question. For ImageNet, you distilled a deterministic few-step flow model into a MFM, right? Not a regular multi-step flow matching model.
Yes. So we took a pre-trained flow map model and we distilled that into an MFM. Though the procedure for distilling like a multi-step flow matching model would be really similar. They actually first distilled a multi-step flow matching model into that flow map. But yes, you're completely correct.
And if you have your flow map here for all these numbers that you're putting, is this with single step inference?
Yeah.
Okay.
So we showed one step, two step, and four step, I think. But yeah.
Okay, I see. All right, then Peter, thank you very much. And I like the power of the Peters. And now, what will we get with them collaborating? Let's see. Very exciting. If you have any last words, then let's go with them now. Otherwise, thanks for joining.
No, I think that's it. Yeah, thanks so much for having me. It was really nice being here. Yes, talk to you later then.
Amazing. Then goodbye, everyone, and have a beautiful rest of your Monday.
Thank you so
Enjoy.
much.
See you next
Bye.
week, hopefully.